In the last talk, we were discussing these certain numbers, certain ratios, certain geometries that seem to be special in the history of mathematics, and then also have this big influence on architecture and have had enormous impact on things like the pyramids in Egypt or the work of Leonardo da Vinci. Today we're going to expand that exploration and really look at how, through the history of architecture and right up to our own time, how important numbers, mathematics, and geometry are in creating architectural form. So there are a number of reasons why I think numbers, mathematics, and geometry have been so prominent in creating architectural form. And we're going to, at the beginning here, outline several of those reasons. And then we'll look at the way that plays out in different buildings. So I think sometimes the reason why this is an important part of making architectural form is that certain numbers in mathematics and geometry are seen as having a kind of mystical quality. There's something very special about them. There's something spiritual about them. And we talked a bit about that in the previous talk, but we'll be looking at mysticism as a reason for employing these in making architectural form. A second thing is sometimes these characteristics simply add prestige to a building. And if you're especially making a kind of new building, you want to be noticed and you want to elevate it, prestige often comes from the use of these elements. A third thing is that, kind of amazingly, all kinds of technical problems like structural stability are actually enhanced by certain numerical and mathematical and geometrical relationships. So sometimes it just makes good technical sense. A fourth reason is that there is something about some geometries that just draws our eye to it, begins to make it iconic, begins to make it memorable in a special way. And sometimes that's a reason for employing these elements. And then the final thing is that sometimes you can use numbers, mathematics, and geometry to create a kind of intellectual puzzle that lets our mind construct and deconstruct the building in a way that just makes it fascinating or interesting. So we do it for mysticism, we do it for prestige, we do it because it just makes technical or structural sense, we do it to make a building iconic, and sometimes we do it to create this kind of intellectual puzzle. So let's see how that plays out. Very prominent in 18th century architecture was this notion of creating utopian communities and making these kind of perfect spiritual forms. So there are two architects in the late 18th century and early 19th century, Etienne Boulay and a disciple of his, Claude Ledoux. This is a project by Boulay, which was a cenotaph for Sir Isaac Newton. Sir Isaac Newton, great physicist, he was making great discoveries about science, about the cosmos, and when he died, Etienne Boulay said, we need to build a monument to Sir Isaac Newton. And so in doing that, he used these perfect geometries because they seem to have a mystical quality to them, a quality that would sort of connect to that science that Newton was doing. So that, which was an enormous scale building, of course, never got built, but you can see the size of people down here. The idea of this great monument to Sir Isaac Newton, based in the sort of mystical quality of the sphere. His disciple, Claude Ledoux, made this proposal for a bizarre house. But a house that, again, this notion that if you lived in this perfect geometry, it would enhance your life. It would make your life more perfect, more full, because there would be this mystical connection to spiritual things. Now, Claude Ledoux took that quite a step further. And he was designing a whole new town, a utopian town in France. And this was fairly popular in the early 19th century, this notion of utopian communities. And in fact, really continued all the way through the 19th century. And in the United States, there were utopian communities. This idea of we're going to make a perfect kind of environment. And then when people live in it, they will lead a more perfect life. So can we find a way to make a physical environment that is spiritually and mystically perfect? So that's what he's trying to do here in this utopian town of Chaux. And in it, it's on a fairly neutral landscape here, but he makes a kind of perfect circle in the center of the town. At the center of that circle is the salt works. That was the major economic driver in the town, the salt works. And interestingly enough, salt, of course, is a mineral that our bodies need to function. So it's a kind of essential life force that's at the center of that town. But also salt, which is sometimes called halite, is a crystal that is a perfect cube. And it's a perfect cube at multiple levels. So at a kind of microscopic level, these are cubes within cubes within cubes that actually make up this mineral of salt. So that geometry, that perfect geometry of the cube, is built into the salt. That's this mineral that our bodies need that becomes the major economic driver of the town of Chaux. So there was salt in the region. That would be where they would purify and manufacture salt for human use. Then around in a circle, around the salt works, are the major institutions of the town. So it would be the schools and the libraries and the museums and those kind of cultural landmarks of the town. And then everything else in the town is again in concentric rings. There are major axes that run through the town. But again, the geometry is very much shaping the core of that town. And then pretty much all the buildings within it are based on geometry. This is the mausoleum, the place where they would bury people, sometimes burials, sometimes ashes. But there is a perfect sphere in the center, and then there are radials that go in every direction, and those would be the passages where there would be columbaria to house the dead. So here we're transporting people to another life. That kind of perfect geometry is an appropriate shape or form for that, because it has some kind of mystical, elevating quality to it. A factory here is made out of a perfect square, and within that crosses that they then make 4 perfect squares here. At the center is again a perfect square. Inside that square is a circle. Each of the corners has a pyramid with an equilateral triangle on the edge of it and a square base. Again, everything in the town aimed toward this notion of perfection through the mystical quality of certain geometries. This is another building type that he explored in the town of Chaux. This is actually 2 different versions of the Maison de Plaisir. So the Maison de Plaisir was a house of pleasure, literally. Basically, it's a brothel. So this is a place for sexual encounter. And for that, what Claude Ledoux would have considered a major function of the city. He does 2 different schemes. One that has a circle that is for circulation around here. All these then little pavilions for romantic liaisons through there. And then a kind of common space, social space for the Maison de Plaisir there. And you can tell in this element right here, again, there's a kind of anatomical connection, maybe kind of in the way Leonardo da Vinci did it in the last talk. We have two kind of ballrooms over here. We have a kind of shaft of space there, and then a head here in the elliptical form there, but all made of perfect geometries. Again, in the other version of the Maison de Plaisir, again, those anatomical references, but everything in series of squares and circles and half circles and ellipses and so on. So geometry, these special geometric forms, again, dictating the shape and form of the architecture. Now, pretty much every building at Show is some sort of geometrical exploration. The square is extremely prominent. He often likes the 9-square grid where you divide it into 3 portions in both directions. All of those creating these fundamental buildings in Show. And again, the notion is these have a mystical quality to them, these geometric forms. And that if we live in those kind of environments, it will make our life more spiritually connected. Now, that's one attitude, one thing that we generate architectural form by a kind of a sense of the mysticism of certain numbers and mathematical relationships and geometries. But another reason I mentioned was sometimes we're just trying to elevate or give some prestige to a particular building. And let's look at a couple of buildings that use math and geometry to do that. So this is a library in Stockholm, Sweden by Gunnar Asplund, done between 1920 and 1928. Gunnar Asplund, premier architect in Sweden at the time. In your readings in Rasmussen's book, Experiencing Architecture, you'll encounter Gunnar Asplund several times. The challenge here was to build a new central library for Stockholm. And this was a very important building for Stockholm. The Swedes have their own language, and Swedish is not a large language. It's not spoken by very many people, but it's a very precious thing to the Swedish people. They like their language. They also like the literature that's come out of that language. So the library is a collection of all of these Swedish language books, and in Stockholm would be the largest kind of collection of these Swedish language books. So they're making a very precious and special building in their culture. And in order to, it's not a large building particularly, but in order to elevate its presence in the city, to give it prestige, he kind of boils it down to a rectilinear or squarish base, and then a big rotunda at the top like that. So it's a square in plan, a square within that square, and then a circle inside that. And that circle is then made into a drum, which becomes the iconic or special form of the building that adds prestige. And there's a really remarkable thing in the experience of this building. You go in down here, and you rise up the stair like that, and you actually enter that reading room in the center of the circle, so that when you rise up, you're able to see that circular form all around you. And it is a kind of awesome thing to come up that stair. Right in the center is this circular chandelier, and you look around and you see 3 tiers of books all the way around, and the whole thing is given an elevated, prestigious feeling by the fact that it's got this perfect geometry to it. And then there are reading rooms around that complete that square on the outside. A second example of the same kind of prestige that's given by certain geometric forms. This is the Guggenheim Museum in New York by Frank Lloyd Wright, done between 1956 and 1959. This is one of the last buildings Frank Lloyd Wright completed before he died. He's a very old man at this point. He's in his 90s. And yet this is one of his most well-known and most admired works, done at that very, very senior point in his life. Again, the story here was that Simon Guggenheim, this wealthy New Yorker, was very interested in modern art. And he had gone all over Europe, which is where kind of modern art was being born in the 1920s and 1930s. And he'd made a great collection of the work of early Picasso, Braque, Leger, Kandinsky, Klee, and he'd collected these paintings. He believed very strongly in their revolutionary power to transform art, but they were not understood very well in the United States. And in art circles in the United States, they didn't have as much presence as Solomon Guggenheim thought they should. So he hires Frank Lloyd Wright to design a museum where he could exhibit this fantastic collection of modern art. And it's right on Central Park in New York, right on Fifth Avenue, very prominent location, relatively small site, but in the midst of this city, it's random collections of all kinds of building forms. But what Frank Lloyd Wright is trying to do is give particular prestige to this site, this building, this collection of works, to elevate their presence in the art world in New York. And he does that by simplifying this building down to these very clear geometries. So he takes the whole site, he divides it into a grid of squares. Inside of each square, he puts a circle. He then generates the larger circles of the building's form there and there. Adjacent to this circle is an equilateral triangle, which is a kind of stairwell. There are circular forms that are bathrooms, lozenges made of two segments of circles in various parts of the building. But the whole building really primarily organized and created by these geometries. And then in the center of that space, that circle becomes a spiral, so that the idea is that you take the elevator up and then you slowly work your way down the building, spiraling down this ramp and seeing the exhibits of paintings as you go down. Completely, mind-boggling, powerful space in the center, again, made much more powerful by the simplicity of the geometry there. And there's really not much to the buildings besides the geometry. He makes all the surfaces very spare, very clean, in order to emphasize the clarity, the kind of perfection of these circular geometries within the building. And again, it created a building that had great prestige and distinction, and housing this collection that then was elevated by that prestige and became a real landmark in New York. And it was extremely successful. This building really made a point about the emergence of modern art, the importance of modern art in life in New York in that period. So there are mystical qualities that make us drawn to certain geometries and relationships in architecture. There are elements of geometry that add prestige to buildings. Another thing I mentioned is that sometimes it just makes good technical sense. And those geometries are there to solve kind of practical problems. An example of that is the geodesic dome. So this is the US pavilion at the Expo in Montreal in 1967. This was a World's Fair. At that point, these World's Fairs were really popular, and every country was vying with other countries to make the most beautiful, most iconic and important pavilion for their country, to draw attention to what their country was doing in the world. So in this case, the United States is building this spectacular pavilion in Montreal to house its exhibits. Bucky Fuller, who was the architect and engineer for the building, had invented previously this idea of the geodesic dome. The geodesic dome is a perfect spherical shape, and then within that, it's tetrahedral geometry that makes this kind of space frame that makes the span. The idea of the geodesic dome is to use the minimum amount of material to make the maximum span. And it turns out that that perfect geometry is the solution that helps you use the minimum amount of material to make the maximum span. And in this case, you see that tetrahedral geometry of the space frame as it's making that great spherical form. Inside the building, the exhibits that the U.S. was touting were our accomplishments in the space race. So there were Mercury capsules. It was really demonstrating the United States' superiority in space exploration. So inside are a lot of exhibits of space-related kinds of things. It also, because all of that was glass that was enclosing the space, it had to be tempered somewhat from heat gain. So there are little shade elements that go in that tetrahedral geometry in order to not get excessive heat gain. So there were photosensors on them, and when the sun would strike it, the shade would come out, and when the sun would go away, the shade would retract. So when the sun came out from behind a cloud, all across there would go click, 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 and all of it would sort of lock down and get shady. And then when the sun went behind a cloud, and you no longer needed that shading, then it would go click, 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 and it would all open up and give more light on the inside. It was a really kind of magical connection to the sun and the cosmos and space exploration and the shape of that geodesic dome and the technologies that were built into it. It was quite an extraordinary building. And then inside it, where they were showing the Mercury capsule as if it were falling from space and about to drop into the ocean, they're showing it with the parachutes. And of course, a parachute is in a section of a sphere, so it's got that same geometry. And why is the parachute that shape? Because it's that shape to resist the air and to get the maximum resistance in a balanced way to bring that down to the ground. It is that geometric shape. So you see that technical, performative quality of the sphere in the building, in the structure, in the air resistance, in many different elements within the building. So that was that great, made a huge span across there with just this tiny amount of material in that tetrahedral geometry. So sometimes we use geometric forms just because they make technical sense in the building. And then we also mentioned that another reason is to kind of create intellectual puzzles, have us imagine kind of constructing and deconstructing buildings, all their pieces and parts fitting together. An example of this is the work of Peter Eisenman. Peter Eisenman is at this point especially, kind of an oddball architect who is very, very enamored of numbers, mathematics, and geometry. And he's a young architect. He's exploring these houses. Some of them have clients, some of them don't have clients, but he generates, I think, like 18 houses in his early career. And they're all based on numbers, mathematics, and geometry and these kind of puzzles. His notion was that, people can live in anything. A house doesn't need to respond to function. It can just be this kind of thing you look at and are curious about, and it really has more to the form really being an intellectual thing. So these houses were not driven so much by function as they were by these mathematical puzzles. And he didn't call them, they might have had clients like the Jones house or the Smith house or the Wynn house or whatever. But he didn't call them that. He called them house 1, 2, 3, 4, 5, 6, 7. So again, showing that allegiance to numbers and mathematics. So in designing a house, what he would do is he would start with these perfect geometries, like the square. And then he would look at subdividing the square, let's say in a 9-square grid. And he's looking at how that might make planes in one direction and planes in another direction. So I can find pieces and parts of these manipulations that I might want to use. There then would be columns that could be at any of those intersection points. He's also looking at making shifts. In this case, he shifts at 3 feet. So then he can make combinations of planes of different lengths, volumes of different lengths, columns in different locations, using that shift. And slowly he's creating this kind of puzzle of architectural form that is going to end up being a house. I think that one was house 2, which we'll look at in a minute. I think this one is house 6, where now he's looking at intersecting that square with planes in 2 directions, and then certain rules for how those planes are manipulated, and lots of little slots and zones within that that are created by the thickness of these planes that go through it. Now there on house 2, this is a plan of it. We start with the square. We do the 3-foot shift that you can see right there, and stairs and kitchen cabinets and things like that go in the 3-foot shift. There's a short square, a double square, a triple square there, and the residual of that becomes a terrace on the outside here. Everything in plan and section, where the windows are, everything about the building is determined by that kind of geometry. These are 2 others. I think this one is house 5 that we're seeing right there, where obviously he moves a square at 45 degrees to another square, another kind of game he's playing. This one is house 6 with those planes that cut through, and you can see that the form of the house just has everything to do with that geometry and that geometrical game that he's playing. Everything articulated by how it fits in that role of the larger game. This is the master bedroom, for example, and in it there needed to be a slot that went through right here. Doesn't make any sense functionally because that's the middle of the room, but that's where in the mathematical game, that's where that zone needed to be. It meant that you really couldn't put a king-size bed in the master bedroom. You have to have 2 twin beds. It means that if you're not careful when you hop out of bed, you're in a slot that actually goes down to the living room below. But all of that is not driven by function. It's driven by this mathematical puzzle. What we see over here is not a stair. That is a geometric form that you happen to be able to walk up. And just to make it clear that that's not a stair, he flips it, and here we see the upside down version of that, which of course you can't walk up, but it's to make the point that it's not about making a functional form, it's about making these geometric pieces that are manipulated and twisted and turned and relocated to make this house, more or less. So the final reason for using numbers, mathematics, and geometry as a generator for architectural form is to make a building that's iconic. And there are characteristics of this geometry that just lock our eye. We just are drawn to some geometries. In this case, this is a school of design in Essen, Germany by Kazuo Sejima. Her firm is called Sana. She's one of the most prominent living female architects. In this case, it's an old industrial environment in eastern Germany, and they're making this new campus out of it. And the design school wants to be this very iconic building, this focus of the campus. So she makes a perfect cube, and then within that perfect cube, she makes windows that are squares. And again, each window kind of focusing your eye on something in particular, so that it's always using that quality of the square that makes it iconic, makes it concentrate your attention in a certain way. So over and over in the building, that geometry is used to create these iconic places, iconic objects, iconic views. The whole thing is a great icon for the whole neighborhood around and the campus, where it becomes this perfect cube in the center. So those reasons why we use numbers, mathematics, and geometry, and you can see the whole range of the way that plays out in making buildings. I want to close with this building by Lou Kahn. We've already looked at several buildings by Lou Kahn. We looked at the Bryn Mawr dormitory that he did. We looked at the Kimball Museum in Fort Worth. In this case, this is a very well-known building he did that is the national capital of Bangladesh. That was done between 1962 and 74. As you can see, a very long period to build it. Part of the reason for that is that it was originally commissioned when there was East and West Pakistan. When they made the partition of the British colony in South Asia after World War II, they separated India and Pakistan by the territories that were more Muslim, which became Pakistan, and the areas that were more Hindu and Buddhist that became India. And those were not contiguous in the case of Pakistan. So there was East Pakistan and West Pakistan, and they didn't connect. So the idea is there would be a capital of each of those, and the government would reside half the year in Islamabad in West Pakistan, and half the year in Dhaka, which was in East Pakistan. And Lou Kahn was commissioned to do the national capital in Dhaka for East Pakistan. And because the government moved, there was housing that was related with that, so the whole ensemble of government would move back and forth every 6 months. Now, the remarkable thing here is that there was then, at a certain point, a revolution, and in the middle of building this building, Bangladesh, a new country, pulled off from Pakistan and became independent. So East Pakistan became Bangladesh. And they had this half-finished Capitol building, which was the old government they were revolting against. In a certain way, it would have been perfectly logical to just dump it and forget it, tear it down, because it was the old government. But there was something so remarkable in this pure kind of timeless geometry of that building that it simply transferred to Bangladesh. And the new government and the people embraced it as an emblem of their new country. And it was completed as the capital of Bangladesh. Now, there are all of these things we've been talking about that can apply to this building. There certainly is a quality of mysticism in the building. The mandala is a very important element in this culture, this geometrical, centered mandala, which has been in that culture for centuries. And he definitely based the building in the notion of that geometric mandala. And the plan is very much generated by that. And it is oriented north, south, east, west, and it has these kind of pure geometries in it. It's oriented north, south, east, west, but you can see that little element right there is slightly twisted, and that's because that's the mosque, which was a part of the Capitol building. But the mosque needed to face Mecca. Mecca was to the west, but not precisely to the west, so it tilts slightly in the direction of Mecca. And then you can see that it's a dodecagon, a 12-sided polygon in the center. Each of these elements are squares. There's often then a square pulled out at the corner of the square, which is a little courtyard. There's half circles and squares and golden rectangles all the way through the entire building. These are used as a way of creating prestige. It certainly reads as an important, prestigious kind of building in the landscape. They're also used as a means structurally. Those arches actually are arches that carry loads down on either side of that triangle. So In a technical sense, they're performative as well. It certainly is an iconic form as a whole, but also has these kind of iconic moments, as we saw in that design school in Essen. And as a whole, it's so elevated by this notion of the geometry. Clear, perfect, pure geometries, bold, simple geometries. And again, like the Guggenheim Museum, or in some ways like the pyramids, there's a kind of eternal and strong verity of the building that simply comes from the fact that it is based in numbers, mathematics, and geometry. So these two talks have really been about how you can't understand architectural form without understanding how deeply it's rooted in this history of the science of mathematics, in geometry, and all of the explorations that have been done in this area for eons. See you next time.